In this meetup, we're basically going to go over vanilla deep learning neural networks for classification and regression. And so if you want to know the link to our material, that's over here. All the stuff for this, for today, is now on the instructional Google Colab, which you can find at that link if you want to follow along. And I would encourage you to also type along with me in by going into Google Colab and setting up a Colab environment. And in case you guys don't know how to get to Google Colab, you just type it into a browser. Come over here. You'll probably have to log in with a Gmail account or something, and then you can create a new notebook. And once you have created a notebook in the Google Colab environment, these are the dependencies you will need to install. That last one, pip install Hurst, we're only going to go over that if we go over all the material pertaining to vanilla deep learning neural networks for regression and classification. And actually, you probably won't need this one for today.
Could you explain the packages?
Sure thing. So actually, even this one you wouldn't really need. So Tensorflow is the deep learning package which we're going to use. It's what our organization is named after. And then the Hurst package is going to be something we'll get into if we still have a little bit of time. It's a way of measuring the long-term dependence of data. It allows you to measure the long-term dependence of data. And so using the Hurst package, you can actually determine whether it is appropriate to use a standard recurrent neural network or a LSTM network. And again, we're going to go more into detail with that when we go into recurrent neural networks, which will probably either be next meetup, or maybe we might go a little bit into it this meetup if we have time. Do you guys still need to type in these dependencies, or have you typed them in? Okay, great. So these are the libraries we're going to want to use. We don't need RPy2, I don't believe. And there are also two forms which we're going to go over today. We're going to go over the sequential models and the functional models. There's not much difference between sequential and functional models. Functional models are just more flexible than sequential models because with deep learning neural networks, you basically have these layers composed of all of these nodes. And the neat thing about functional models is that you can actually connect one layer here and one layer towards the bottom of your model and connect them together. Whereas sequential, it's just one after the other after the other. So you can make all kinds of creative, flexible connections with functional models that you can't do with sequential models. And again, I'll show you what a sequential and functional model looks like. And Sherpa is a hyperparameter optimization library. We will most likely go over it next meetup, although we might take a look at it this meetup as well. And then what we're going to want to do is we're going to want to load these data sets. From scikit-learn, we're not going to use the data sets in the earlier part of the Colab. Those were just used to show you how to import data into the Colab environment and put it into a format which the neural network can understand. I would say that in my experience making neural networks, 80% of the problems I got were problems related to actually getting the data into a format which the neural network would accept. Because neural networks are very picky about how they want the data when they receive the data. And so once here, this is an example of the sequential model. It's just this input layer, and then it immediately goes to this dense layer, and then it goes to this dense layer, and then it goes. And the numbers here denote nodes in our dense layer. The more nodes you have, generally the more parameters you will have in the model. But that having more parameters is not necessarily always a good thing. And again, when we get into hyperparameter optimization, I'll show you how you can create a program which will actually be able to determine the optimal number of nodes in each of our dense layers. But for right now, we're just using an arbitrary number of nodes in each of our dense layers. And then I should probably explain this. Batch normalization is something we use to prevent overfitting in our models. It kind of renormalizes the tensor data between each of these, between the output of the dense layer in this case and the input of the next dense layer. We want to avoid overfit models because those are generally not generalizable to new data. We don't want a model which has learned our training data really well, but isn't applicable to new data. And so that's what batch normalization helps protect us against. And then you might have also noticed Atom, the optimizer we're using, that's a pretty standard default optimizer. Most people use it. I'm using mean squared loss error. Again, it's just, I've found mean squared loss error is most convenient for me whenever I'm working on deep learning neural network. The standard is a slightly different, the standard default loss function is a slightly different loss function known as mean squared error. Yeah, I don't know. Mean squared loss error just works a little bit better for me. And then in model.fit, what we're doing is we're feeding our input data and our output data. In this case, we are doing regression. So we are using the input data to predict, to fit to the output data so we can predict new output data. In this case, since we're plugging in house prices, we're basically trying to make a model to predict house prices so that we can then predict future house prices given some input data into our model. And this validation split is basically telling the algorithm to split it 80-20. So 80% of the algorithm will be the training data to train the model, and then 20% will be used to determine how accurate the model of the model is. In other words, it'll be split into training and test data by an 80 to 20% proportion. And then finally we do our prediction. And if we have a model summary here, and we see our predictions are outputted. This is the final loss. It's not a bad loss. So these are the this is the summary which we get from this model.summary line. It's showing us the number of parameters, and this is the graph showing actual housing prices to predicted housing prices. So we see that the model is very good, judging from this graph, at determining what the actual housing price is, since red is predicted and blue is actual. And but there are some things which we can do to our data to better prepare it for our deep learning neural network. So, for example, and I covered these things which we could do in the previous lesson, but I wanted to show you these things which you could do to your data to get better and faster convergence. I wanted to actually show it to you so you could see it kind of in action. So the first thing which we can do is we can actually have a min-max scaler. And what min-max scaler does is it compresses all of the values in the data to a value between 0 and 1. And that oftentimes leads to faster convergence and lower error in the model after fewer iterations or epochs. And the epochs or iterations which we do to train the model are listed here. And so, let's see, the value loss was 0.044. So if I run this again, we should get a okay. Interesting. Well, I will get a corrected version of that, of this collab posted soon. But basically what you would want, I'm not entirely sure why it's throwing that error, but it shouldn't be. If all I'm doing is doing a scalar fit transform on the data, so I'll have to figure that out. But what we would have seen if we had done the scalar fit transform is we would have probably seen faster convergence to a lower error rate with the same number of iterations. And so it's important that you do things like PCA or principal component analysis and min-max scalar to your data and apply those procedures to your data before you feed it into your neural network, because you want to do as much of the work and as much pre-processing of your data before you feed it into your neural network in order to maximize the performance of your neural network. Principal component analysis, by the way, is where you kind of, the theory behind it is that you shift the axis to maximize the correlation between the x-axis and the y-axis. That is actually immensely helpful. Principal component analysis is in order for it to construct a model which is accurate to the data. And then next we'll want to go to our classification example. Now, one of the things you'll see here is you'll see a sigmoid activation function. So the sigmoid activation functions are generally what are used to in classification algorithms in order to get the correct convergence to with our classification algorithm. And basically classification algorithms differ from regression algorithms because with classification algorithms, your job is to take some data and figure out which bucket that data belongs in. And you're supposed to determine this based upon your training data, where it specifies which bucket each data point belongs in. So yeah, you need to use the sigmoid activation function in the output. You'll also notice that the last layer of our model has 3 nodes and not 1 node, and that's another 3 nodes is significant because it specifies how many buckets are actually in our classification algorithm. And you'll also notice that this is not written in the sequential model format. So this is actually the functional model format. And the neat thing about this is that you can theoretically connect this layer to this layer. Whereas with the sequential model, it would just go this one, this one, this one, this one, this one, this one, or this one, this one, this one, down like that, step by step. And finally, with regression algorithms, it's not always that important what the loss is. You can play around and figure out which loss is best for you. With classification algorithms, you will generally want to use the categorical cross entropy if you are doing classification with more than 2 buckets, so basically 3 or more buckets. And you will want to use the binary cross entropy if you are doing doing classification with 2 buckets. And but otherwise our classification algorithm looks more or less the same as our deep learning neural network regression algorithm. So we do the epochs, and then we get our model summary, and that's basically how that goes. Does anyone have any questions so far? There's actually another cool component which I wrote down here about principal component analysis, and that is that you can actually add an n components argument to the PCA. And what that'll do is it will actually get rid of the variables in your data which have the least amount of correlation to the other variables in your data. So this is a really good way of getting rid of variables in your data which basically don't impact your output at all and therefore wouldn't be useful to your model. So that's another cool thing about principal component analysis. And there are also a lot of other things which you can do, which we covered in lesson 1. So you can do Windsorize to get rid of outliers. You can do, let's see. Oh yeah, you can do, instead of taking the values themselves, you can take the derivative of the values, so you can take the change of the values. And the funny thing is that these deep learning neural networks actually have an easier time handling the difference of values and making predictions of the difference of values or how they will change than they have about in terms of making predictions about the values themselves. One example I can give is that, like, if you're trying to measure something like, if you're trying to do predictions about something like GDP, instead of doing constructing a deep learning neural network which just tries to predict what the total GDP will be next year, you can have it predict the GDP growth, or how the GDP, what percentage the GDP will change, and that's actually easier for the algorithm to do than making predictions about actual values, is making predictions about how values will change. So that's one thing you should consider doing when you're constructing deep learning neural networks, is putting in as inputs, instead of the actual values, how those values change, and instead of the output values, how those output values change. Especially during regression, that's very useful. So that's pretty much, if you guys don't have any questions, that's pretty much what I have for, in terms of deep learning neural networks for regression and deep learning neural networks for classification. I'll just give you a little preview of what we can of like recurrent neural networks and hyperparameter optimization and that kind of thing. So the first thing which you have to actually understand about recurrent neural networks is that recurrent neural networks are used for data where it's time sensitive. The data is time sensitive. So with vanilla deep learning neural networks, it assumes that there is no, it doesn't matter how the data is ordered. But if you're working with time series data, suddenly it does become important how the data is ordered. You can't just jumble data from 1926 from data from 2018 with data from 2000. That would be very bad. So for time series regression especially, you will want to use recurrent neural networks. And a recurrent neural net, and there are different kinds of recurrent neural networks. So there are basically vanilla RNNs, and those basically just keep the data ordered and assume that the data is ordered from top to bottom as when they're doing the model. And that one data set value will affect kind of the other data value. But LSTMs are more interesting, and they are useful for things like text regression. So predicting what a person wants to type out, for example, or what a person will type out, for example. And LSTMs are long short-term memory cells, that's what they stand for. And those are used for any kind of time series data where there is long-term dependence. So where the predicted value is going to have a very heavy dependence on even values which occurred well before it, not just right before it. And so one of the ways you can actually measure the long-term dependence of data, if you're not working with text regression, for example, if you're just working with other kinds of numerical data, is through the Hurst exponent. So just give me a minute. I'm going to actually have to pull up the Hurst library from one of my other. So we don't actually have any kind of data in here right now, but if we did, then this would print out a coefficient looking something like this. And the way Hurst exponent works is that a Hurst exponent of 0.5 means that there is no long-term dependence in the data. Values which occurred well in the past have no bearing as to output values which will happen in the future. A Hurst value below 0.5 means that there is an inverse correlation. So data values which happened way in the past or values which happened way in the past are actually inversely correlated to values which will happen in the future. And then, so they have like almost a negative correlation. So if you think of it like, for example, stock data, that means that if two stocks are inversely correlated, that means that every time one stock goes up, another stock goes down. That's how you can think of inverse correlation. And any value which is above 0.5 means that there is a positive correlation between past output values and future output values. So if it's significantly below 0.5 or significantly above 0.5, this coefficient right here, then you are going to want to use LSTM neural network, LSTM layers and LSTM neural networks. If it is very close to 0.5, like 0.49 or 0.51 or something like that, or then that means that there's almost no long-term dependence in the data, and you can just use a vanilla recurrent neural network. And then I just would want you to take a look at this. We're not going to go too much into depth into this, but we're going to save this actually for our next meetup. But there is a library for what's known as automatic hyperparameter optimization, known as Sherpa. And now you might be wondering what hyperparameter optimization is. So hyperparameter optimization is basically where you are trying to optimize how many nodes there should be in each layer, what kind of optimizer to use, that's a hyperparameter, what kind of loss function to use, what kind of activation functions to use, how many nodes are in each layer. Those are all hyperparameters. And with automatic hyperparameter optimization, you can actually figure out which sets of hyperparameters are the best hyperparameters to use in order to construct the model which will best fit your data and give the best predictions of future data or do the best kind of classification. And the thing which is used here is to do the hyperparameter optimization, which I think is preferable, is Bayesian optimization. Scikit-learn also has a hyperparameter optimizer called grid search. But what you have to understand about grid search is that grid search is extremely slow. You're basically trying to figure out almost by brute force which hyperparameters are the correct hyperparameters. So Bayesian optimization, which Sherpa allows you the option of doing, is actually the best kind of hyperparameter optimization you want to use to get the optimal hyperparameters for your deep learning neural network to construct your model. And again, that's on the that's under the Sherpa library, and that's pretty much all I have for today.
And will you, I guess, post on the Meetup when you update the area?
Yes, yes. Yeah, I don't know why it's doing that. It should work even with a scalar fit transform. I'll have to figure that out when I get home and fix that.
How do we know what your next meeting will be? How and when?
You'll want to look on meetup.com under Seattle Tensorflow.
Okay.
I will post the date and time of the next meetup there. Or you can look on the Microsoft Reactor Redmond website
Okay.
and check the calendar there too.
Okay.
I have been trying to secure a space in Seattle for us. The problem is that we have about 88 members, which is not considered big enough by Google for them to give us any kind of room there. So we will be hosting our meetups there and here at least until we get big enough, basically, that we can get a room in Seattle.
So how many more do you, more members do you need? 200 or?
I talked to the Google people and they did not specify exactly how many more members I needed, but I know that TensorFlow Seattle has close to 1,000 members, and so I think at least I'll check back on them when we have maybe over 200 members. Did you guys find this useful?
Yes, definitely.
I like your summarization of PCA better than what I've heard before. A little more succinct.
I was wondering if you can comment on the packages that you commented out actually.
Yeah, sure thing.
Yeah, and what they do. All the packages that were commented out in the talk.
RPy2 was just is just an interface between Python and R. I don't actually know how to use it. I was just trying to do some stuff with it to see if I could do any kind of Python R exchange, but I haven't figured out how to use it yet. Yeah, so this is the package for doing PCA, and then this is something called kernel PCA. I'd urge you guys to check that out. It's a kind of a non-linear PCA, so to speak. TensorFlow probability. Okay, so I guess you could say my passion is actually combining probabilistic deep learning or probabilistic programming with deep learning. And the reason is because when you have regression algorithms, they just produce outputs, they produce predictions, but you don't know the uncertainty with those predictions, right? So this is like if you go to if you're a weather forecaster and you just say it'll rain today, instead of actually being able to attach uncertainty to that weather forecast, being able to say there is a 55% chance that it's going to rain today. You know, I think that's it's extremely important to be able to attach uncertainty to a prediction. And if you can't do that, then you won't be taken seriously outside of computer science if you're trying to use deep learning neural networks for other things. So one of the things which I hope to cover in a future meetup is something called a Bayesian neural network. And what that basically does is it actually allows you to quantify the uncertainty in your predictions. And the best part is that it doesn't assume that the uncertainty in the predictions follows a standard normal distribution. And that's, I think, is really important because if you look at something like individual stocks, for example, one of the interesting things you'll find actually is that returns for stocks do not always conform to a standard normal distribution. They have skewed distributions, and those skewed distributions come from what I was talking about earlier, the fact that these stocks oftentimes have long-term dependence. So if you use standard financial models, those standard financial models will assume that there is no long-term dependence with the stock, and so they'll assume that the error, the values which the returns can take follow a standard normal distribution. But they have found that these individual stocks do have long-term dependence, and that when they have long-term dependence, it's no longer a standard normal distribution, which quantifies what values the stock can take. When I was still in high school, I kind of got my start in all of this by building stock trading algorithms on Quantopian, so that's why I have a bias, you know.
Is that pretty close to explainability for deep learning networks? The probability? Is it also used to kind of explain how deep neural networks work?
No, not really.
Explainability.
Yeah, so that's the problem with deep learning neural networks is they're basically, the models they produce are basically black boxes. You can't, it won't tell you why the model is doing what it's doing. Yeah, that's still a major problem with deep learning.
Have you came across Jim Summers with Renaissance Technologies, who's a professor at mathematics at MIT?
I have not come across him, no.
The reason I brought him up is because they're a very successful organization, and he's got about 300, with 100 of them PhD qualifications, and they bring in a tremendous amount of money, and they discovered that over the years they were very successful in futures and commodities, but the stock market was a very difficult one.
Yeah.
And so they came across, they did finally, Jim Summers just kept pushing on it, and he has came up and found that there is a relationship between keywords that are related in the stocks, that are related in news, that, and then also the number of them that are related to analysts who are making recommendations. And if you get a series of analysts making recommendations,
Yeah.
then you have a strong correlation for movement in the stock.
Yeah, yeah. Yeah, I've heard of people when I was doing my Quantopian stuff. I heard of people doing sentiment analysis, and yeah.
So that's where I'll be heading.
I suppose I haven't introduced myself yet. So I'm Sabarno. I am the organizer of Seattle Tensorflow. This is actually our second physical meeting. The first physical meeting happened in January, and it was the first meeting I did since it's the first physical meeting this organization has had, and also the first meeting I did after I took over as organizer for TensorFlow. I found out that before I was organizer here, there was another guy who was organizer of Seattle TensorFlow, and he was based out of New York. So he did like webcasts, but he never held physical meetings. Let's see here. I guess I'm 19. I'm a college student. I actually just I just got out of high school last year. Yeah.
So where are you going to college?
Bellevue.
Is it appropriate to ask what everybody else is into?
Oh yeah, sure thing. Yeah, if you guys want to share.
Pivoting, my name is Knock, hello. I'm pivoting in my career to go into data science. My background is primarily in education and forensics, and I just really enjoy working with data, so I thought it was the correct pivot for me.
Similar story to Knock, but my background was in public accounting and finance.
Yeah, so I was a government employee before I came out here working for the NIH in accounting, trying to get into data science. I actually came out here originally thinking I'd do software development, decided that was more of a hobby thing, I think, for me. I like data science better, so that's what I'm doing now.
I'm recently doing a lot of log-related analysis, so I could take it any way I want. It could be a time series, or it could be just data analysis and some predictions based on past data and predicting future data, and then trying to figure out problems with the systems.
Yeah.
Based on recurring and frequency of events that happen.
Yeah.
So I'm just looking at ways to kind of do a bit more predicting and alerting when system problems happen.
Mm-hmm. Yeah, that's interesting. Do you guys want to, in a future meetup, go over clustering algorithms? Because strictly speaking, deep learning neural networks only cover classification and regression. They don't cover unsupervised clustering. So we'd mostly be working with scikit-learn if we covered clustering algorithms. But if you guys are interested, I could do that for a future meetup. Okay. Yeah. I'll do that for a future meetup then. Is there any other thing in which you guys are particularly interested in covering?
Right now, I don't know off the top of my head.
Would it be appropriate to tell you what my interest is if I send you an email? Is that appropriate?
Yes.
Okay, and your name and everything is on that site?
Yes, in
Okay.
meetup.com.
I
Yeah.
will give you my direction and interest in how I got there.
Yeah.
I started in neuropsychology because I have a degree in psychology, and I had courses in neuropsychology was my first interest 50 years ago.
Yeah.
And then from that point, I just kept moving on and getting more intensely into neural networks and neural systems as they are applicable today.
Yeah. That's interesting.
If it makes money, it's great.
Where's the way?
Thank you.
Yeah, thank you very much.
Thank you.